All right, so now we are working on um, the next topic, which is slope and tangent lines. Um, as you read on this next page in the notes, Theorem 10.11 has an important consequence. So if the graph of r equals f of theta passes through the pole when theta equals some angle alpha, and f prime of alpha is not zero, then the formula for dy dx simplifies as follows. Um, so the f of alpha cosine alpha and f of alpha sine of alpha become zero. And then the f prime of alphas cancel out, and you're left with sine alpha over cosine alpha, which is equal to tangent of alpha. So the line theta equals alpha is tangent to the graph at the pole, 0, alpha. So tangent lines at the pole, if f of alpha equals 0 and f prime of alpha is not 0, then the line theta equals alpha is tangent to the pole to the graph of r equals f of theta. All right. Let's work on plotting some graphs for the following polar curves. I'm going to show you here how I would like for you to approach this. You could technically make a table of values and plot dozens and dozens of points and then finally figure out what figure you're dealing with. But instead, I'd like for us to know a few simple problems and how to deal with those sort of as a memorized thing, because it really is the easiest way to graph some of these. And then others, I'm going to teach you a way to use what you already know. So let's look at this one. We discussed r equals a cosine theta earlier. Remember, what that means is that it's a circle. And because it's cosine of theta, we know that the center of the circle will be on the x-axis. If this were in a rectangular world, which is kind of the graph that I'm drawing now, is sort of a amalgamation of both. It's got the rectangular nature to it with the axes I started with and the polar nature to it, as evidenced by the circles I'm drawing that are concentric about the origin or the pole. All right, so if you recall, there is a point on the pole every time you have r equals a cosine theta or a equals sine or a times sine theta, and the diameter of that circle will be a. So the diameter of the circle is 6, and so with one point at the pole, if I move along the x-axis, because it's cosine theta, 1, 2, 3, 4, 5, 6 units, that will be a point that's on the circle as well. Then, if I go to pi over 3, where cosine of pi over 3, of course, is 1/2, at pi over 3, 6 times 1/2 will be 3. So put at pi over 3 a value of 3, and at negative pi over 3, we also have cosine of negative pi over 3 is equal to 1/2. So 6 times 1/2 is 3. So those are a couple of good points to do. And then once you have those points, do your best to draw a nice circle. Try to make it look circular as best you can. Like that. All right. So that's what I would want you to sort of just know and memorize. Now, for problem B, r equals 2 minus 3 sine of theta. All right, I'm sorry, I was a little bit distracted for a second. My apologies for that. Move move this down a bit. Okay, what I'm going to suggest on this one, and many of the graphs that I'm going to ask you to learn how to do, is to rely on prior knowledge. If we rewrote this as if it were y's and x's, like this, y equals 2 minus 3 sine of x. Producing that graph is something that we're supposed to be able to do from pre-calculus. So I'm going to remind you a few things about how to do that. So we're going to graph this in a rectangular grid as if that's what we were supposed to graph. And what doing this will do for us is it will inform us about an infinite number of possible points that we could plot. Instead of making a table of values, we're making a graph of values. So, because it's sine of 1x, that implies that the period will be unchanged. And so the normal spacing on the x-axis that I would expect that you know to do is every pi over 2. That's kind of an expected every quadrant marking is generally pretty good. And on the y-axis, we'll make that 1. All right, so the 2 in that equation is an indication that we're moving everything up 2 units. And so I call this the baseline. The baseline will be at y equals 2. So this is kind of like a fake x-axis, if you will. We've shifted everything up 2 units. Then the 3 implies that our amplitude is 3, which means make sure that you've allowed for 3 marks above the baseline and 3 marks below. And if you look at this kind of ahead of time with that in mind, you notice that I put exactly enough marks above because I knew what was coming. You'll get better and better at this, by the way, as you review it from your pre-calculus experience. Okay, then starting the sine of 0, which is 0, we'll move that up 2 places so that we'll have a point on the baseline on that fake x-axis. Then normally we would go up to the high from there, but because of the negative in front of the 3, that'll reflect the graph over the baseline, and instead of going to the high 3 above the baseline, we'll go instead to the low, which is 1, 2, 3, below the baseline. The next point will be a middle point at the baseline, then a high value of 3 above the baseline, middle, high, middle, low, middle, high. It's something I'd say a lot to my pre-calculus classes because this is sinusoidal. Those are the major points that we're going to try to incorporate into our graph. And that gives us a pretty good idea of the graph of this function. Now, let me, oh, wow, that was not straight. Let me try again. All right. It was kind of straight. It wasn't vertical. That's what I meant to say. Now, the y, remember, is replacing r. So if you look at the y values, the highest is 5 and the lowest is -1. So we need to make sure that we, if we're drawing this by hand, that our number of circles takes us out to at least 5. And of course, if you're doing this on a given grid, then you'll be able to use the given grid and its spacings. I am going to suggest that unless there's a really big, huge number that's kind of beyond what you're normally working with, that every circle represent 1 away from the pole. You can make it a different value, but for anything that I ask you to do, that should be sufficient. All right, so there's our grid, and sorry, it took me a little while to draw it, but hopefully it's going to be a nice one that we can actually plot points. Okay, so recall that x is replacing theta. So at angle theta equals 0, our output is 2. So right on the polar axis, we're going to move out 2. Then, looking at our next major point, it's at pi over 2, which of course where the positive y-axis would be, and the answer there is -1. So if we're on the positive y-axis with an r value that's negative, that means we're going to go backwards and plot a point on the negative x-axis 1 away. Now, in between those 2 points, there are an infinite number of points that we could use to think about plotting this, but one of the most important is that point where it crosses through the x-axis. I may or may not know exactly where that is, and I don't think that that's really the most important thing. But we do know that at some point the radius will be 0, which means we go through the pole. Now, to guide our graphing between the very first point we graphed and the one represented by the x-intercept on our rectangular graph, realize that the r values are decreasing. So we're going from 2 to 1.5 to 1 to 0.9 to 0.4 to 0.3, all those numbers. So what I'm going to do over here is starting at 2, I'm going to make the radius decrease as the angle goes toward pi over 2. And there I'm going through the x-intercept. And now the answers have become negative until we get out to -1. So that part of the curve, let me get a different color here so you can see what I'm trying to refer to. That part of the curve that we just did is the representation that I just drew in that yellowish orange color. That corresponds to what is on your polar grid over to the right. Okay. So continuing. The next major point on our graph is at pi 2. So we go to the angle pi, which is the negative x-axis, and we're out 2. Well, what happens is, again, there's an x-intercept, so we've got negative values as we go from pi over 2 to pi, negative values to start with, which are over here in the quadrant behind the other side of it, the one that's pi away from it, until we go through the x-axis, which is the pole, and then the r increases and increases and increases until you get to 2. Okay. All right. Now, that's working pretty well. So we've now finished the pi over 2 to pi part of our graph. Now, the next major angle is 3 pi over 2, and that's where we get out all the way to 5. So 3 pi over 2, the negative y-axis, we go out 1, 2, 3, 4, 5 units and put a dot there. And in between the point, excuse me, the point at pi and 2 and 3 pi over 2 with 5, the radius is just growing. So draw a nice smooth curve where the radius gets bigger and bigger and bigger and bigger and bigger and bigger until it gets out to 5. Okay. Now, the last is at 2 pi, will be at 2. And at 2 pi, we're back to the positive x-axis. We're at 2, so we get back to the very first point that we plotted. And the radius is decreasing, so very smoothly draw a curve such that r is getting smaller and smaller and smaller and smaller, like that. And this graph is called a limicelle. My French pronunciation, I'm sure, is wrong, but hopefully you'll forgive that if you actually speak French. Otherwise, you'll go, well, that sounds pretty good to me, because you have no idea either. That's all right. This is called a limicelle. This is a limicelle with an inner loop. I'm not going to require that you memorize that name or that the equation that looks like this produces that graph, although you can approach it that way. I would prefer that you approach it as we did with your rectangular graph with x and y, informing you about a bunch of ordered pairs on the polar graph to be plotted. That's the approach that I'm going to suggest that we take with graphing in polar. All right, so let's look at another example. This is C. R equals 4 sine of 3 theta. Okay, so we'll use y equals 4 sine of 3x to graph this. Now with that 3 in front of the x in the argument of sine, that's going to change the period. And so I'm going to do a little bit more discussion about period because last example it wasn't changed, so I didn't want to talk about it very much there. But the formula to find the period of a sinusoid is to take the normal period, which is 2 pi, and divide it by the absolute value of the number in front of x, 3. And the absolute value of 3 is 3. So the period of this function is 2 pi over 3. Then, if you'll break that into 4 equal parts by dividing the period by 4, that will inform you on your rectangular graph how to space the marks on the x-axis. So that results in 2 pi over 3 divided by 4 is pi over 6. Okay, so in this particular equation, there's no vertical shift, no new baseline. And so the only issue that we need to pay attention to besides what we've already talked about is that the amplitude is 4. All right. So the baseline is going to remain on the x-axis. So the x-axis is the x-axis. Make sure that you're going to be able to go above the baseline, the amplitude of 4. So make at least 4 marks on the y-axis in both directions. And then every mark on the x-axis is going to be spaced pi over 6 apart from the others. So every one of these represents another pi over 6 that we're moving. All right. So sine of 0, when x is 0, it'll be sine of 0 is 0, and so that'll be a point on the baseline. The next point will be a high value. So at pi over 6, we're expecting the high value with an amplitude of 4. That high value will be at 4. Then back to the middle. Then a low value, -4, middle, high, middle, low, middle, high, middle, low, etc. Get enough of those going so that you can produce the graph. Produce enough of the graph to get an idea of what's going on. You may not actually use all of these points. It's good to do a good cycle of the sinusoid, and a little bit more won't hurt. Not necessary all the time, but it can't hurt in this situation. Okay. Oh, wow. I really need to be able to draw verticals better. Let me try that one more time. All right. So there's our XY axes. The positive x-axis is the polar axis. And we're going out to 4. So I'm going to make sure I get 4 concentric circles spaced out, each space being representing 1. So I'm making sure I get out at least to 4. You can draw extras if you want, but This is painfully slow, I'm sure, for you to watch, so I'll do just the minimum required. All right, so our very first point at angle 0 is 0. So we're at the pole. Then, by the time we get to pi over 6, which pi over 6 is about right here, we should be out at 4. So 1, 2, 3, 4, put a dot at angle pi over 6 out 4. By the time we get to 2 pi over 6, which is pi over 3, so about right here, we should be back to 0, which is the pole. And so what happens in between those is, starting at 0, 0, the radius is increasing and increasing and increasing as we go further and further out around the, from 0 to pi over 6. As we go through those angles, as we go through these angles here, the radius should be growing outward. Then they're going to start decreasing and decreasing and decreasing until by the time we get to pi over 3, we're back to 0. All right, so for the third mark, 1, 2, 3 pi over 6, which is pi over 2, of course you know where that is, it's up here. By the time we get to pi over 2, we should be at negative 4. So starting at pi over 3, we start getting negative answers. So between here, pi over 3 and pi over 2, we're getting negative values. And as we get those negative values, looking at where we're headed at pi over 2, we're expecting an answer of negative 4, which is going to be way down here for a negative value for pi over 2, the r being negative for pi over 2. We're getting all of these negative y values that are getting further and further and further out toward the negative 4. Then the next major mark, 1, 2, 3, 4 pi over 6, which is 2 pi over 3, it's about right here, we should be back to 0. So we're between pi over 2 and 4 pi over 3, we still have negative values, but they're headed back towards 0. Then get to the next mark, 1, 2, 3, 4, 5 pi over 6, we should be out to 4. So 5 pi over 6, we're out to 4. So about right there. And the radius is increasing between those two angles until we get out there. Then 1, 2, 3, 4, 5, 6 pi over 6, which is pi, we should be back to the pole. So we're going to decrease our radius values between 5 pi over 6 and pi until we get back to 0. And looking at this as a final product, I'm kind of ashamed at how my pi over 6 and my 5 pi over 6 look like they're really at kind of different angles, and they should be the same. If you do this on a graphing calculator, it comes out to be pretty pristine and perfect looking, but by hand, I totally get how this would be harder. Now, on a test or something, I would provide you with a grid. And so knowing exactly where pi over 6 is and 5 pi over 6 is, those will be easy. You'll be able to see those as actual radial lines on the grid. So please pardon the imperfect nature of this graph, and we'll just move on from there. All right, the next page talks about several different ways. This is the other way you could learn how to graph polar graphs. Oh, excuse my dog. The other way you could learn to do polar graphs is to memorize a bunch of forms of the equations. And like the very first one, you have values of a and b. And like r equals a plus or minus b cosine theta. Depending on the values of a and b, you're going to produce different types of graphs. Limicons with a inner loop like we did before. Cardioid is a heart-shaped graph. A dimpled limicon and a convex limicon. Those are all possible. to memorize and figure out, well, if A over B is this, then this is what it should look like, and this is, going to inform me. You can do all that memorization. I just wouldn't. I would graph the rectangular graph like we just did and use that to inform you about points on the polar grid to do. So you can, take a look at the next page or two with all of those formulas. And if you feel like doing that, you can certainly memorize all of those. I wouldn't. One thing I do want to point out, though, is that for the rose curves, this is kind of interesting to kind of know what to expect. What we just graphed was a rose curve. And as it turns out, if n is odd, like we did here with 3, your rose curve will have that many petals, 3 petals. So if you look at the third one over, r equals a sine of n theta, where n is 5, you have 5 petals. And that would help you know that you're finished graphing. When I got 3 petals, I knew I was done. However, if n is even, you get twice as many petals. So when n is 2, you get 4 petals. When n is 4, you get 8 petals. And so that's kind of an interesting thing to know, and it'll help you know when you're done. And then the next line, circles and lemniscates. The circles, that's the only 2 that I would ask that you memorize are the first 2, the circles that we've already discussed. R equals a cosine theta, R equals a sine theta. You can do that from a rectangular standpoint, but it'll take you more time than just memorizing those 2. The lemniscates we probably won't encounter much, so I wouldn't worry about those. The other thing I would suggest is that you know that if it's a rose curve, when n is odd, you'll get that many petals. When n is even, you'll get twice as many petals. Okay, that ends this lesson. Thank you for paying attention, and I will talk to you in class.